And another remark I want to make, this is that if the dimension of the module M over D is finite, so D is a division algebra with the conditions as we have there, and R is a dense subring or subalgebra of the endomorphisms of M over D, then R is simply the endomorphism algebra of M over D, and this is simply a matrix algebra over D. So if the module is finite dimensional over the division algebra and the algebra is dense, the only possibility is that you have the whole matrix algebra. So this is an easy exercise. If the module is finite dimensional over D, you take simply a basis here, because you have the linear algebra over a division ring. This is the same as the linear algebra over a field. You take a basis, and you take any set of elements, and you can send them by element of the ring to the corresponding pair. So this simply means that you get all the matrix algebra. And now, before to state the Kaplanski theorem, I want to mention and to use the density theorem This is the Chevalier-Jacobson density theorem. Which states that if R is a primitive ring or algebra and M, this is a simple, faithful R module, and D, this is the endomorphism of algebra of the module of the M module R, then the algebra R is a dense subring or dense algebra of the endomorphism algebra of M over D. Of course, this theorem, I don't want to prove this theorem. This is one of the basic theorems in ring theory. And there is a nice proof, for example, in the book by Jacobson, also in the book by Herstein. When I say the book by Herstein, I have in mind the non-commutative ring theory. But one consequence, or this is one lemma of this is the following: if R is primitive and M is a simple, faithful R module, and D, this is the endomorphism algebra of the R module M, then you have two possibilities. Either R is isomorphic to the matrix algebra over D for some n, or for any n there exists a subring of R such that R n maps on M and D. Map means that this is a homomorphic image of this. So the proof of this lemma, this is really easy. This is simply if the dimension of M over D is less than infinity, then by this remark which I had here, this simply means that R is isomorphic to, R is dense, of course, is dense in the algebra of endomorphisms over D. And by this remark, this is simply isomorphic. R is isomorphic to the matrix algebra over D. And in the second case, if the dimension of M over D is infinite, we choose M1, M2, Mn to be linearly independent over D, and we consider Rn to be the ring, to be the subring of R, containing all the elements such that R of Mi is a linear combination of M1, Mn. So this is easy to see that this is a subring, and it maps in a natural way. So it's a subring which maps naturally on M and D. You simply consider this as a the mapping is, you have simply here this element, this is a base of the n-dimensional vector space, and corresponding element, since this is dense, for each n-tuples of element there exists an element from the R which maps these elements to the corresponding set of elements. So this simply means that the element R behaves as a matrix of the matrices, as n by n matrix over the division algebra. But of course, maybe you have some kernel, so this is. So I also, in order to prove the Kaplanski theorem, I want to use some more algebra, which is okay, not for the undergraduate course, but this is not PI-Algebras, so I'll simply state the results without proving. You see, this is of course not the case, but you remember when the classification of the simple groups was announced, it turns out that this is too big, maybe about 8,000 pages or I don't know, and they decided that this is too much, and they decided that half of this or even more half, this is a general group theory. So here I'm cheating in the same way. Some things which I want to use. This is not PI, but this is from some other branch of algebra which is accepted officially to be not as in the case of groups. So, of course, the algebra R is simple if it has no two-sided ideals. Two-sided ideals. Of course, different from 0 and R itself. And if K is the center, okay, maybe I see that K is my base field, the center of R, then in this case, assume that C is a field, and we call in this case that R is central simple K algebra. And I'll state a lemma, and I'm not going to prove it. This is if R is a central simple, okay, this is C algebra, of course. sorry. If okay, it's a central simple C algebra, and L is a field extension. Sorry, a field extension. Then the tensor product R and L over C is also a central simple, but this is L algebra. If you want to imagine how it looks like, you can choose a basis of R over C, you can choose a basis of L over C, and the tensor product, it consists of the formal products. The basis is formal product. So this is the way to prove physically that this is a central simple algebra. And the next lemma, which I don't want to prove again, although it's more complicated. If G is a division algebra with center C, and L is a maximal subfield of D, then the tensor product of L and D over C is dense in the endomorphism algebra of D as an L module. And we have two possibilities, and either A, the dimension of L equals n, the dimension of D over C equals n squared, and then the endomorphism of the algebra over L, this is simply the matrix algebra over L. Or the other possibility, we have that the dimension of L over K is equal to infinity, and also the dimension of D over C is also infinity. So you see, if you have a division algebra with center C, of course the center is a field, and by the Zorn lemma you can find a maximal subfield of D. Of course, D is, the maximal subfield is not in the center already. It contains the center, but it's not central because if D itself is not commutative. And then you know that if you extend it's a standard construction, for example, in the theory of fine dimensional central simple algebras, that if you take the tensor product with the maximal field, you get, okay, this, you should be proved that this is dense here. But in the case of fine dimensional algebras, you know that in this case the dimension of L over C is equal to n, the dimension of the field of the division algebra over C is n squared. And if you consider this algebra here, it becomes the matrix algebra over the field. So this part here, this is from the theory of central simple fine dimensional algebras. Here, this one is a little bit more complicated, but nevertheless, this is. So I have 5 minutes to state and to prove the Jacobson, the Kaplanski theorem.